Hello, this is Iestyn Russell-Hughes, and I'll be your presenter today. So the contents of the course are up on the screen. Hopefully everybody can see them. So essentially the webinar is split into two parts. We've got a section on log conditioning and a section on petrophysical evaluation itself. So without further ado, let's go into the start of the presentation. So by way of sort of explaining a little bit more about things before we jump in, when I've been working as you've just heard as a petrophysicist for 25 years or so now. When I joined ICON about 9 years ago, it kind of became apparent that the way I've been doing petrophysics wasn't really fit for purpose for the rock physics that was being done afterwards. So this presentation is really a sort of overview of some of the things that we've seen, some of the adaptations we have to take to make sure that our petrophysics is done in the way that helps with the rock physics evaluation. So as mentioned here, in order to get the most robust rock physics evaluation, the petrophysicists should have some understanding of the rock physics workflow and adapt their interpretation accordingly. The key inputs for rock physics are density, compressional sonic, and shear sonic, and so they need to be available and in good condition. Equal emphasis is required in the reservoir and the non-reservoir for volume of shale computation. Porosity from density is a crucial thing for rock physics methodology, as we'll see. There has to be equal attention to the fluid properties in invaded and non-invaded zones. Extending the petrophysical interpretation beyond the interval of interest is also very useful, as we'll see. Consistent approach in evaluating the multiple wells should lead to a reduced uncertainty in the analysis of the rock physics results. So why does this matter? Well, the Petrophysics and Data QC section is the first step in any sort of workflow that goes through rock physics modeling, rock mechanical properties, trend analysis, well ties, seismic conditioning, seismic conversion, so on and so on. So if you get this bit wrong, the impact will be seen in all of those things. So you need to make sure you can get this done as correctly as you possibly can. Otherwise, you can lead to issues down the line. So the first thing we'll talk about is the log conditioning. So it's standard practice to edit your log data prior to petrophysical interpretation. Now, this should be done by everybody who's doing petrophysics. So the things that normally are done, depth shifting, removing log data acquired in casing and below first reading, removing any erroneous data, so any tool failure, cycle skipping on the sonic and so on, flagging any bad hole, and removing the data affected by that bad hole, creating a composite log set over the entire well by splicing together the logs from each run. So you have one continuous log for each type. That's kind of the standard sort of workflow that a petrophysicist should follow prior to actually doing any petrophysics or anything else with those logs. So the first thing I want to talk about here is log QC itself. So the log data you may have can come from a variety of places. So this could include the field tapes, the DLIST files, LAS files, a corporate database that you've copied the data from, some other software package that you've loaded it from. So it's crucial that you QC your log data to make sure that the data you're looking at is correct. So it's from the correct well, for starters, and has not been modified in any way. So in this example, you can see a scanned image in gray, and the red curve is the digital data which has been superimposed on top of it. So here we can see, if you can see my cursor, this upper section here shows that there's some depth shift has been done to the log, which may not be an issue in itself if it matches with something else from another run. But the crucial thing to look at is this section in here, where we see the log has been edited in a different way from the original log. So has this been done deliberately? What's going on here? So this is obviously, maybe it's an error in the digitizing, but it's more likely someone's gone along and edited it for some reason. So, you know, these are the sort of things that can catch you out if you take that and then carry on forwards with it without knowing what has been done to the data. So next we'll look at casing and casing effects. So here we can see a well panel with various logs on it. So here we've got the gamma ray and the caliper log, and shading is to the bit size. Here we resistivity is in the next track, density in a neutron, and then a sonic log. So the upper section here is the section that has been logged in the casing. So this is not reading the rock, this is reading the casing. So it needs to be removed prior to doing any work with this data. Below that, you can see a section which has been affected by Rugo's hole. So essentially it's washed out. So that is reading the mud, not reading the rock. And again, you probably want to remove that before you do any further work with the data itself. So your actual engaged log data probably only starts around about here on the density, for example. Okay. Next, first reading. So we looked at the casing, which is the top of the log run. At the bottom of the log run, your first reading is where the data starts to be read properly within the well. So prior to the first reading, the tool is sitting at the bottom of the well bore and has been switched on, but it's not actually reading correctly. You're not moving the tool string up, so it's just sitting there. So you need to make sure that anything that's been recorded below that first reading point is removed, so you don't splice it to another section below if they've drilled a deeper section, for example. So the first reading for each of the tools is different depending on where it is on the tool string. So here we can see an example of a tool string, and each of these tools is in a different place. So the first reading for these is in a different place. So you can see the first reading here for the density log is lower down than the neutron, and then the gamma ray one is a little bit higher up. You can also see these on the logging service run, normally listed as various depths within there. So you just be aware of those and edit it accordingly. Depth shifts. So it may not be so much of an issue with more modern tools where everything can be recorded under like a supo combo or so on, but quite often with the older wells, you have various runs of service runs over the same interval, and quite often these are off depth with each other. So you need to do some depth shifting to ensure everything is on depth, all the peaks and troughs line up. So in this example, you can see we have a gamma ray in the first track, and then a sonic and a resistivity log, which are all aligned, and then you can see the raw data from the density and neutron log in the next track along, which are offset. So we do some depth shifting to fix that by stretching and squeezing so that they all match up. So that's the idea. Now you may find that something like LWD or MWD data has more problems with depth shifting issues than wireline does, but it still needs to look at it and make sure that everything is on depth. Tool sticking. So another common problem, when you're requiring data, sometimes the tool gets stuck in the hole and it affects the log reading. So you can see here in this display, we have in the last track, we have something called tense, which is the tension. Oops, sorry, jumped. Tension log, and that shows where the tension increases on that, where it goes to the left. That shows an increase in tension, and that means that the tool is stuck. So here we can see, sorry, my cursor's there. So as the tool comes up, it gets stuck and the tension increases, then it gets free and jumps back down. And the same thing happens here. Now you notice the effect of the tension on the logs is in different places. So on the resistivity logs here, the effect is pretty much the same place as we see it on the tension. On the density, it's a little bit higher up. On the neutrons, higher up again. And on the gamma ray, it's up over here. This is because the tool is in a different place on that tool string. So where the tension is seen is at the base of the tool, as we can see here, and the effect of it on different logs is that bit further up the tool string, so that bit further up the log. Hope that makes sense. So that was sort of general sort of log conditioning issues that you may come across. So now we're going to focus a bit more on the sort of things that rock physicists may be interested in. So that is the key inputs into the rock physics logs, the density and the acoustic logs. So again, we emphasize this again, erroneous log data must be removed. So get rid of anything that's bad hole and so on. Density logs susceptible to bad hole condition. So you can use the caliper and the DEVO as a guide and edit it accordingly. You may have multiple acoustic logs acquired over a logging run. So look at all of them, pick the best or create a combined one as you need to. Ensure that the logs are all on depth, as we just seen, and any gaps that you feel you can leave in the logs, you can always fill using trends that you may have derived from your rock physics models. So synthetics that you can create from multi-well trends, you can go back and fill the gaps with those. That we find is the best way to do any gap filling. So here's an example of some bad hole condition affecting the density log. So in this display, we can see I've also calculated a bad hole flag, and the bad hole flag is based on the decal, which is the difference between the caliper and the bit size, and the DRO log. So we use a cutoff on that to sort of create a bad hole flag from 0 to 1. We use this as a guide, not as a de facto, that's bad hole, that's not bad hole. Just as a visual sort of guide to it. But you can easily see, if you look in the last track, the red log is the edited row B, and the gray dashed log is the original. So you can see where the edited log exists and where I've edited out where the gaps are, where you can see that the density has been affected by the bad hole. Okay, so that's a little bit on the bad hole. Now we're going to talk a little bit more about acoustic logs. So acoustic logs, primarily DT and DT shear, but the DT itself, acoustic log devices have been around for quite a while now. So from the 1950s, we started measuring it with using single receiver transmitter type tools, going into the 60s, 70s, 80s, and more sort of borehole compensated log type tools, long space sonic. Then going into more modern tools like the array tools, which essentially the tool design has improved accuracy of velocity measurements by minimizing the borehole effects, and obviously measuring additional acoustic wave properties like the shear and Stoneleigh. So here's a little diagram of the kind of thing we're talking about. So in the first sort of diagram on the left there, this is the original patent from Schlumberger, and we can see that we have some individual listening to a tool going up and down in the hole. It didn't really work as far as I understand it, but the patent is in, so there we go. So that's kind of evolved from there to borehole compensated tool, where you have a series of 4 transmitters and receivers, and you take an average from that. And now we have these much more modern things like the sort of array tools, where we can measure cross dipoles and all that kind of thing. So let's first talk about sort of general sort of acoustic log QC. So here we have an example of an older tool where we have 4 sonic logs that have run off the same tool, and these measure the DT long space, DT long space near, and a DT long space far, and they're all displayed in the track here. If you can see my 3rd track along, so the black, red, blue, and green logs, and each of those logs is reading incorrectly at some point in that section. So you can't just choose one and go with it. You have to try and do some work to remove, splice in together, or make something which is a final edited log, which looks like the log on the end, like so. So we've essentially taken sections which we're happy with, which haven't got cycle skipping or weird spikes, removed them and created a final log from that. If we're not sure what the response should be, just leave a gap, because again, we're going to use this in the rock physics modeling. We can go back and fill that gap with some synthetic that we created from our multi-well trends. So the next example is from a more modern tool. This is from a Schlumberger DTI type tool, and we can see here a monopole compressional signal of a coherency, and this is from the receiver and this is from the transmitter. And what happens is that they take those two and essentially take the average to be the final sonic log, the DTCO. Now that's fine where the signal agree. Where you have some disagreement, or some, in this case, some massive disagreement, then you get a really weird response which doesn't follow any of the, so the average is basically, you know, nothing between those two, so it doesn't make any sense whatsoever, and it's plainly wrong. So what we would do as a rule is take the section from each of those which we feel was matching the coherency and splice it to the bit in the next section which was matching, and so on, to make a final log which was correct for the interval. But this just goes to show you need these images are quite useful for QC and always worth picking up if you can, opening if you have a scanned image of it, or if you're lucky enough to be able to get hold of the DLIST file with the process data on it, to load it in, have a look at it, make sure that your coherency matches with the log data that you've actually got. Similarly, when you're QCing the shear, in this example, I've got a DSI tool with a monopole and a dipole that's been acquired. So in the first track, I've got the dipole shear from the lower dipole DT1, and in the second track, I've got the monopole shear and compressional displayed. If we compare the two of them, the two shear logs, the DT4S from the monopole and the DT1 from the dipole, we can see that there's some discrepancy and difference between the two. Now, this is kind of a strange example because in this section, the log that was labeled DTSM, which generally means the best shear log in the run, was the DT1. But when we calculated a Poisson's ratio and VPVS from it, we could see the Poisson's ratio wasn't great over this interval. This is because this reservoir sand within this section was much faster than the overburden and lower burden shales, and so the DT monopole didn't actually acquire anything in those slower sections, but in the fast sand it did. The issue here is one of precision. Because the range of this tool is something like 70 to 770, it's not quite so precise at the faster formation rock, whereas the DT4S monopole one give us a better response and give us a better Poisson's ratio and VPVS in this section. So we ended up splicing in the DT4S into this to make a final shear log over the whole interval. So again, it's worth having a look at all the information you've got and bearing in mind that there may be some issues with precision where you're moving from faster to slower formations. So why is this important? Well, here we can see a little synthetic pre-stack seismic gather image where we've got the measured as is logs compared to the conditioned logs. So you can see that the gathers that have been created from both. So you can see here that some of the spurious reflectors have been removed by the conditioning. It's a lot smoother down into here. Some of the spurious AVO angle offset stuff's also gone from down here. So, you know, you're getting something, you're getting a better answer. It's going to be better for doing things like well ties and so on going forward. So it's important, it's an important step. Okay. So that's the conditioning. So we'll talk a bit more now about petrophysical analysis. So the first thing we'll talk about is volume logs. So a volume of shale can be computed from a variety of log data. Common methods can include gamma ray, linear, non-linear, density neutron, density sonic, SP, resistivity, and so on. So it's good practice to calculate multiple methods and compare on an interval by interval basis. Some volumes such as coal and evaporites can be defined using cutoffs. So they're either absent or they're present, 0, 1 or 0, 100%. Other volumes such as sandstone, limestones, and dolomite may be generated, but it's important to understand how this was done. So before you pick them up and use them in rock physics as volumes, were they done just to create sort of a pretty picture, so for cosmetic purposes, or were they actually calculated as part of the petrophysical calculation in some sort of Elan style probabilistic petrophysics package or something like that? So that would be okay to put in, but something which had been calculated afterwards as an afterthought or as some sort of weird volume of silt or something like that, which doesn't really have a rock physics kind of label. Maybe that is something to avoid putting into your rock physics model. If in doubt, ask the petrophysicist what he's done. So in this example, I'm going to show you, oops, I've jumped a bit, haven't I? No, that's okay. So in this example, I'm going to show you some QC of your volumes of shale that you may have generated. So in the first track, we have a volume of shale from a gamma ray in black, volume of shale from density neutron in red, and a volume of shale from density sonic in blue. Now, the first thing to notice is obviously that they're all kind of reading on depth, which is good, which shows that our log depth shifting and everything else has been done correctly. In the lower section, which we've labeled here as the 40 sandstone, you can see that they broadly agree pretty well. But as we go into the overlying boulder section, we can see there's some discrepancy between the responses. Now, if we look at just the gamma ray log here, we can see that the gamma ray reading at around about this level is broadly the same as the sandstone gamma ray response. So you may think that this is a sand based on just purely the gamma ray log. Now, if you look at the other logs in here, the neutron and density specifically, you can see that the response in here is not the same as the sandstone. So what we've got in here is, in actual fact, as you can see from the label, a tufaceous claystone. The tufaceous claystone is fairly inorganic. That means that there's very little radioactivity in there, which means that your gamma ray essentially is reading it as a sand. So it's just got less radioactivity. That's all that's doing. It's just so that's why you have this discrepancy. So it's worth calculating volume of shale from more than one method to ensure that there's some commonality in what you're seeing, and if there is any differences, try and explain why they are, because it's also important from a rock physics perspective, because you want to treat this shale as a different kind of rock type to this shale. Similarly, in the next example, we have a glauconitic sandstone, which means that the gamma ray essentially doesn't see it as a sand. Actually sees, if anything, it gets more radioactive as we go through the sandstone itself. But in these other log responses, we can see there's definitely something there, a brine bearing potentially, given the resistivity response there, sandstone kind of response there on those logs. So we can see, you know, if you just calculate volume of shale from gamma ray, you're going to miss that sand. Next, I'd like to talk to you about something that's a bit of a bane of our lives, consistency. So here we can see 3 crossplots of 3 wells, cross-plotted together, density versus VP in this case. And in the first crossplot, we're just cross-plotting the data from the 3 wells themselves. The second one, in the middle one, is colored by interval, and the third one is colored by volume of shale. Now you can see, if you just look at that, that third one, there isn't really much consistency in the volume of shale outside of the cleaner sections. This is quite a common issue. So if you have data that you've got from a field over time, you've had Petrophysics run on that as the work was acquired. Quite often, people don't refer back to what was done before. The Petrophysics was done, just to get the results in the reservoir. So there is a lot of inconsistencies there. So we need to go back and look at that and reevaluate those volume shales to make sure that it's now much more consistent, like you can see in this example. So the work's been done. So now we're able to evaluate and derive trends from that data. So we can see here, if we then limit the volume of shale to be less than 10%, we can pull out a nice consistent sandstone, in this case, trend, which is very close to the Gardner sandstone rock physics model default, and increasing the volume of shale to be 80% or over, we can see that that also pulls out a nice trend from the which kind of matches with the friable shale model. That wouldn't have been possible if we were looking at that inconsistent volume of shale there before. So next, porosities. So the porosity log is the basis of any invasion correction and subsequent fluid sub performed on the density or the sonic logs. So the rock physics workflow assumes the porosity is determined from the density. Porosity derived from any other method other than density can introduce errors into these invasion correction or fluid sub kind of steps. In reservoir intervals, it's assumed that the density log is influenced by invading mud. So whether it be water-based mud or oil-based mud, where there's oil or gas present, you should really correct the porosity for the effect of that hydrocarbon. Any core porosity or grain density you've got can provide invaluable calibration points for porosity calculation, particularly where the fluid density is not particularly well defined. So here we have another example. This is a hydrocarbon correction. So we have a nice clean sandstone here, which is gas bearing, and apologies anybody from Shell, so I got the colors the wrong way around from what you're used to, but this is supposed to be gas. Here we can see the apparent porosity is in purple, so that's what the log would give you if you calculated it directly. And we have done a hydrocarbon correction in there to essentially calibrate that then with the core data. So we can see that the correction, that the fluid properties we're using in that hydrocarbon correction match and give us a good match with the core, so we can feel fairly happy that we've done it properly. So once you've done that, the first step really in the rock physics would be then to correct for invasion. So in this example, again, we're looking at a gas, and here we can see what we're doing here is essentially correcting the density and sometimes the sonic logs for the effect of the borehole fluid invading into the rock, and therefore changing the log response back to what it would be in situ conditions. So this would be something probably more covered on in a later talk, but I'll mention it here just as part of the thing. So essentially, if you've calculated porosity from a source not the density, i.e. sonic or density neutron, then you may find that you introduce errors in these steps, in the hydrocarbon correction or the invasion correction, and then fluid sub. Also, something you might need to think about is the oil-based mud. So here we've got an example of 3 wells, all drilled with oil-based mud. We can see that the oil-based mud wells in the reservoir plot like so, just to below the Gardner sandstone line. Now that might be fine, but when we go and look at it, we can see that once we do the invasion correction, it shifts the density log back up towards the Gardner sandstone. It makes us feel that that's probably more likely the true situation. And if we had a water-based mud well in there, we'd be able to see that a bit better. Unfortunately, I don't have one in this example. So porosity is calculated from 40 sandstone here and several wells in the North Sea. So the crossplot on the left displays the apparent porosity of the sands using constant fluid densities in all the wells, just as they are. Crossplot on the right shows the porosity derived from the same sands using fluid density values which correspond to what we believe to be the fluid mix in the invaded zone. And you can see that that corrects all those quite nicely. So now we're able to then easily define a compaction trend through those, which we wouldn't have been able to do before. So this example is just to show you again the problem with the porosity coming from any other method other than density. So this type of rock physics model, the modified Hashman-Strickman, is a VP versus porosity model. If your porosity comes from essentially the VP, then you're just doing VP versus VP, and you're not really going to see any proper trends and things in there. It's just going to reflect on itself. Okay. Next little section is about extending your interpretation beyond the interval of interest. So normally the focus of the petrophysicist is the reservoir interval and the hydrocarbons content thereof, and as it should be. But this can sometimes lead to logged sequences outside those intervals of interest having a cursory evaluation, or in some instances no petrophysics interpreted there at all. So in order for the rock physicist to produce synthetics to compare to seismic data, it is necessary to extend the petrophysics interpretation beyond the interval interest. So if possible, all overburden and underburden should be evaluated to assist in the creating of a good well tie. So iterative approach. Petrophysics informs the rock physics, but rock physics also informs petrophysics. So V-shell computation is more uncertain sometimes, where you've got no obvious end members present. You know, if it's a silty section, you don't really know what the sand or the actual pure shale is. The rock physics can actually help further refine that petrophysics for you. If you're looking at trend analysis, which show a good match exists between input logs and synthetic logs, or whether there's further improvement is required. So in this example, we see that. So we've got two panels here, one initial and one updated. So the initial, what we're looking at here, it's probably a bit difficult to see the actual trend lines, but the blue log is the original log, and the pink magenta log is the synthetic that's been generated from the trends. So we can see in the first example, the initial, that it's doing okay until it gets down to the middle section where the synthetic doesn't really match with the original logs. So what we did here is we went away and had scratched our heads and thought about it a bit more, and looked back at what we'd done in the petrophysics and realized that maybe that section needed to be a bit cleaner, and also we'd left it as kind of quartz. We kind of changed it to be a more marley carbonate dominated sequence, and then once we reran that, we got a much better match with the synthetic, which gives us a happier feeling about the rock physics models, and also a more robust petrophysical analysis. Deliverables. So generally what you get from your petrophysicist are composite logs, a volume of shale, a porosity of saturation, reservoir summations, pay flags, and so on. What you probably should also be getting, especially if you're going to be doing any rock physics or any further work that kind of way, is condition, density, and definitely sonic logs, and particularly the shear if you have it, something that generally petrophysicists won't look at as part of their normal routine day-to-day. The shear log tends to be passed aside because it's not actually used as an input in any petrophysical analysis, so it's worth hunting that down. Also, you need to get what petrophysical parameters were used in the analysis, because quite a lot of the petrophysical parameters, like the shale points, the matrix points, what fluids are used, and so on, you're going to want to reuse the same things in your rock physics modeling, and also what methodology was used. Did they calculate the porosity from the density? Is there any sections where they've switched to sonic for whatever reason? How have they calculated their different volumes, and so on? So as we've seen, for petrophysics, for rock physics, you need to think about conditioning your log data and focus on your density and your acoustic logs. Volumes log computation, you need to think about where the other volumes are coming from, but you can calculate from more than one log for V shell. But if you compare the results to make sure that they're the same, or at least that you can understand where the differences are, make sure that the porosity is from the density, as porosity from other methods can cause problems. You need to make sure that you correct the porosity in the fluid for fluid effect in the invaded zone. You also need to extend the interpretation beyond the interval of interest where possible, and an iterative approach is key. And that is the end of the presentation from me. So I guess, thank you very much.